Chapter 1, Real Numbers. And numbers, tell us about values or quantities. For example, if you say you have 1 rupee, then the number 1 tells us about the amount of or value of money that you have, which is 1. And if you say you have 2 apples, then the number 2 here tells us the quantity of apples that you have, which is 2. And in your previous grade, you have learned a lot about numbers. And if you notice there, then we were not really interested in numbers as values or quantities. Rather, we were interested in numbers for what they are. We were interested in numbers for numbers being numbers. Just like we are interested in a car. Well, you can use a car to get from one point to another point, but that's how we use a car. That doesn't really tell us much about the car. A car is something in itself. Even if you don't use it, it would still be there. So we have to, if you want to learn more about a car, we have to look at the car. We have to learn more about it, not how we use it. And that's what we want to do here. We want to learn more about numbers. And just like a car, because it is useful and makes our life easier, numbers do that too. They help us solve many real life problems, and they are useful for making our life easier. And we are going to learn a lot about them. Not a lot, but we are going to learn some fundamental things about numbers that are going to help us understand them better. And numbers are of two types: real and imaginary numbers. And the very category of numbers was invented or was created to tell real numbers apart from imaginary numbers. And real numbers are numbers that it's any number that you can come up with. And imaginary numbers are, these numbers are not imaginary in the sense that we imagined them or invented them. Even real numbers were invented because we needed them. But imaginary numbers are, well, the term is kind of a misnomer, but these numbers are not really numbers that tell us about quantities. Rather, think of them as some kind of tool that mathematicians have developed to solve problems. So they are not really, or you can say they are numbers, but not numbers like we would imagine real numbers. And in higher grades or when you go to university, you will learn more about imaginary numbers, how they are used and how they are used to solve problems, especially in electrical engineering. So we are not going to focus on imaginary numbers here. Rather, we are interested in real numbers. And real numbers are of two types. First, rational. And rational, comes from or is derived from the term ratio. That means in P by Q form. And if you can express a number in P by Q form, then that number is called a rational number. For example, 5. So you can always write 5 as 5 over 1. And then you can take 3 over 4. So this number is already in P by Q form. And then you can also express decimal expansions in P by Q form. And decimal expansions that I can express in P by Q form are of two types. The first one is finite decimal expansions. That means these decimal expansions will terminate at some point. For example, 1 over 5, 5 over 4. And if you expand 1 over 5 decimally, then it is going to be 0.125. Well, here you can have a very, very long decimal expansion, but somewhere it will end. So you can always express that decimal expansion in P by Q form. Then we have an infinite decimal expansion, but there is a pattern in it. That means there is a repeating pattern in its decimal expansion. So you will have certain numbers. You will have a decimal expansion. Then, there would be some random numbers, but then a pattern would emerge, and you could see it. You can see it in this kind of expansion. For example, 1 over 3 here, it's a very simple one here. The decimal expansion of 1 over 3 is 0.3333. So 3 repeats itself, and it can go on it can go on. It's non-terminable, but there is a pattern to it. And this kind of expansion I can always express in P by Q form. Then we have irrational numbers. So irrational numbers are numbers that are not rational. That means I cannot express them in p by q form. And if you look at the term irrational, then this means something illogical and not sensible. And in a moment you will see that the literal meaning of this term can also apply, or is appropriate for these numbers, that these numbers are irrational. I mean, they don't behave. I mean, these numbers are not like numbers, don't behave like numbers. I mean, they are unnumberly, so they are irrational. And these numbers are always infinite decimal expansions, but of non-repeating nature. And just think about it, your decimal expansion just goes on and on and on, and there is no pattern to it, just like we saw in the rational numbers. So when you have a random number or an unpredictable number, or you do not know what the next number is going to be, you can't really predict it, then it's really difficult to put this number in p by q form, to obtain two values, p or q, that would get us this number, because this number just keeps taking a random value, and as long as it keeps taking a random value, you can't really pin down these integers p and q, and that's why they are irrational. I mean, they don't behave sensibly. But the term irrational is not because they are irrational, it's because they are not rational. And these numbers are square root of 2, 1 over square root of 3, square root of 3, pi, square root of 5, square root of 7, and so on and so forth. And rational numbers can be further divided into many other categories. For example, natural, whole, prime, integers, coprime, composite, and many other. And we are going to look at them one by one briefly. Natural numbers. So natural numbers are all the numbers that you can use for counting. For example, 1, 2, 3, 4, 5, 6, and so on. And 0 is not a natural number, because you do not use 0 for counting something. Rather, we express something which is absent, or which isn't there, by 0. So it's not really we use for counting, rather we just show that it doesn't exist. So it's not really counting. It doesn't express something that is there, it expresses something that isn't there. So not really something we are counting. Then we have whole numbers. Whole numbers are numbers that are whole or complete. I mean, they express the idea of something complete, full, not fraction or decimal. So you can say 1, 0, 1, 2, 3, 4. Let's say you'll say I have 1 apple, 2 apples, 3 apples, not 1.5 apple. That's a part of apple. We are not talking about a part of apple, rather just 1 apple. And 0 is a whole number, because you're saying that it doesn't exist, but yes, it's nothing, but it's nothing not in parts or not in fraction. If it's nothing, it's totally not there. So it's completely not there. That's why it is a whole number. And then you have integers, and integers are whole numbers, but they also include negative counterparts of whole numbers. For example, they can be -4, -3, -2, and 0, 1, 2, 3, 4, and so on. And integers, unlike natural whole numbers, they give us a lot of flexibility in talking about numbers, because you can express, let's say you have 2 rupees, then natural whole numbers can just express the amount or value of that money, that is 2 rupees. But an integer can tell us more about that money. For example, if you lend 5 rupees or if you borrow 5 rupees, then using integers I can tell more about that money, whether you borrowed it or lent it. Let's say if you borrowed it, then I'll put it as negative, because somewhere down the line you are going to give it back to someone you borrowed it from. And if you lent it to someone, then I'll say it's +4, because somewhere you're going to receive it in future, and it will be in addition to your wallet. So integers are numbers that there are whole numbers, but they also give us a lot of flexibility in using them, telling us more about the context of numbers, that how they are used, where they are being used. Then we have prime numbers, and prime numbers are numbers that are greater than 1 but have only two factors, 1 and itself. For example, 2, 3, 5, 7, 11 and 13. And 1 is not a, by this definition, 1 is not a prime number. Why? Because it doesn't have two factors. It has only one factor. Well, technically you can say it has two factors, 1 and 1, but the problem is both the factors are same, so essentially they're 1. But the prime numbers are numbers that are not divisible by any other number than itself. So by this definition, 1 is not prime, but if you look at that, it has two factors, 1 and 1 itself, and it's not divisible by any other number, so it can be prime. But for here we won't consider it a prime. Then we have composite numbers, and composite numbers are numbers that are not prime, so they have more than two factors including 1 and itself. For example, 4, 6, 8, 9, 12. You'll always have a number other than 1 and itself that divides these numbers. And then we have coprime numbers, and coprime numbers are, it doesn't have anything to do with being prime actually. The coprime numbers are numbers that have no common factor other than 1. So these numbers can be prime, but not necessarily. For example, 17 and 35. 17 is a prime number, but 35 isn't. But if you look here, then 17 and 35 have only one factor common, that is 1. 11, 13, 17, this triplet is completely prime number. So we'll go to the next, 33, 34. So 33 is 3 times 11, 34 is 2 times 17. So these are divisible by two numbers, 33 3 by 3 and 11, and 34 by 2 and 17, but they don't share any factor. They don't have any factor common except 1, so they are coprime.